Hello everyone. Today I wanted to continue our discussion on increasing throughput in blockchains, increasing the throughput of number of transactions. And we've looked at two things so far. We've looked at Bitcoin NG. And the idea there was that you have two types of blocks. You have key blocks and you have micro blocks. So the key blocks essentially are going to decide who's going to be the leader. So if you think of a BFT type of protocol where you have a leader, and the leader of course decides what transactions go in which order. Okay? So Satoshi was doing everything in one shot, and what the Bitcoin NG folks were trying to do is to split up some of the functionality. So they said you have these key blocks which essentially is doing leader election. And after this, the leader is allowed to generate micro blocks. And then of course the next leader comes along, and so on. So we saw that there were some issues that because only these key blocks had proof of work, there is a temptation for the next leader to point directly to the key block. He doesn't have to point to these because he might be greedy and want the transaction fees in these transactions, right? All the transactions in the micro blocks. So this that was an issue. So we said we have to do some tricky things like sharing the transaction fee with the next person and so on. In fact, more than 50% has to be shared with the next person. So those were some issues, but at least in theory, if everybody was honest, this would give you high throughput. One of the drawbacks of Bitcoin NG was that the allowed hashing power for the adversary decreased. So if you notice, for the two attacks that we considered hashing power of the attacker, which we called alpha, to be something like I think it was 25%. And you can show that you can't go all the way up to 50% for the two attacks that we considered. You'd have problems. Okay? So already that's one of the weaknesses of Bitcoin NG. In Bitcoin, you can prove that up to 50% adversary power is tolerable, but not with Bitcoin NG. You have to be willing to tolerate less adversary power. Right? And who knows what other attacks are possible. We haven't proved that Bitcoin NG is secure against all possible attacks. We just considered two of them. Of course, recently for Bitcoin we have shown, we'll consider that in a later class. For Bitcoin, it has been shown that any sort of attack from an adversary, from a Byzantine adversary, Bitcoin is robust to, right? Provided the attacker's hashing power is less than 50%. So this was Bitcoin NG, and then we said we'll look at some other ideas, sort of as maybe as a prelude to Prism, and we looked at some of my own students' ideas. So we call them anchors and links, and we said that why not reveal the proof of work information more regularly. Okay. So this proof of work generated in Bitcoin comes very slowly, once every 10 minutes or so, and that opens up the system to various types of attacks like double spend. If you release the information more regularly, it makes the system more robust to those types of attacks, right? And so if we think, what are we doing differently here? So here you have leader election, and you have transaction generation, transaction ordering, we can say. These are separated out in Bitcoin NG. Whereas they are actually done together in Bitcoin. So Satoshi did too many things together. A block, when it is generated, automatically says who the leader is. Okay, so of course the leader is the person who's going to put the transactions in a particular order. The block already has transactions in a particular order which cannot be changed, right? And there is another thing actually which Bitcoin is doing, and that is voting for previous blocks. So suppose you have a blockchain, maybe there is a fork, in general you have a large tree. The next block, when it arrives, is voting for this particular block. In fact, it's voting for all ancestors. Right, and here in anchors and links we are partially separating this out. Of course, blocks themselves vote for previous blocks and ancestors and so on, but also the links and the anchors also vote for previous blocks. Okay, so here we have I should say here you have some additional and more frequent voting. Right? So this is slightly different idea, and of course it wasn't directly increasing the throughput. It was making the blockchain more robust, right? Basically it was decreasing the confirmation time. Okay. So there are various things that Satoshi was doing in his blockchain, all in one shot. When you create a block, leader election, transaction ordering, and voting for previous blocks. So what this paper Prism is going to do, Prism came out I believe in 2020. I think it is CCS 2020. Or it could be 2019, and just put a question mark there. So what Prism is trying to do is Prism is trying to separate out all these three functionalities, and they're going to use different entities. So by entity I mean something like a block. Here you have the various entities are anchors or links and blocks. So Prism is going to separate out this functionality, and it's going to use different entities to do that. So separate leader election, transaction ordering, and what else? Well, voting for ancestors, voting for blocks in the chain, let's say. Right, and so Satoshi did all of this in one shot, and he had just a single blockchain. So here there are actually going to be three types of chains or three types of blocks. You have transaction blocks, and you're going to use we're going to use something called proposer blocks. And here you're going to have voting chains. And the claim that Prism makes in its paper is that they come close to the optimal possible for transaction throughput and for confirmation time of blocks. Okay, so theoretically, what is the best you can do? So suppose you have a particular miner, and it has a network link with the capacity C bits per second. Okay. So what is the maximum throughput possible? Well, in terms of transactions per second, well, this is sort of like a data rate, but effectively, you suppose you have a transaction. Every transaction is of a particular size in bits. Then this directly tells you what is the maximum throughput you can get in terms of transactions per second. So maybe let's rewrite this instead of talking in bits per second. Let's talk in C transactions per second. So suppose that many transactions per second can be received or transmitted by the miner. Then the maximum throughput in the blockchain is C. And assuming, of course, all miners have the same capacity, link capacity, then that is the best that the blockchain can give. What about confirmation time? So this is the best throughput So how much time does it take to confirm a transaction? And in Satoshi's analysis, he said 1 hour for a given attacking hash power and so on, right? And probability of the attacker succeeding in a double spend attack. So that was a long time, but what is the best that you can get? So suppose you have a maximum network delay. Suppose this is a particular miner, and we have the network. And we have another miner here. So somebody sends a transaction, and let's say this miner includes it in a block. And what is the minimum time for the network to say, the network of miners, to say that that particular transaction has been confirmed? So suppose we say that this delay is, just use delay is D. Okay. So definitely the confirmation time has to be larger than D. So the confirmation time is larger than D. So here, probably to be more precise, I should say throughput is always less than or equal to C. Okay, so we may not be able to achieve this maximum value of C, right, or this D, but effectively what they're saying in Prism is that your throughput is going to be of the order of C. There may be a constant out here, and the confirmation time is order of D. Okay, so essentially you can get very high throughput and very low confirmation time using their method. Okay. But of course their method is quite complicated, and they use different types of blocks and so on. To look at some of the details of Prism. So we said that we want to split up various functionality of blocks of Bitcoin. We don't want everything to be done in one shot. We want leader election to be separate from transaction ordering, and we want to vote for ancestors in a block in a different way. Okay? And at the same time, we don't want to divide the roles of miners into different parts. We don't want one set of miners, for example, taking care of transaction ordering, another set of miners trying to do leader election and so on. We want all the miners to be doing the same thing, but at the same time we don't want it all to be done by the same, let's say the same set of blocks or data structures. So we want proof of work. We want all the miners to do the same activity, but we want to split up the tasks among different sets of blocks. Okay, so we'll see finally how exactly miners do all of this together. But for let's say to start with, let's look at the different types of blocks. Okay. So the first types of blocks are called transaction blocks. And these are generated over time. You can have these transaction blocks getting generated. So each transaction block can be large. It might have, let's say, could be 1 MB large even, right? And these are generated continuously by the various miners. But these transaction blocks themselves don't have any particular ordering. Each transaction block is not necessarily pointing to a previous transaction block, Okay, so it's sort of like each of these is independent, and they don't have any particular order. Okay, so it's possible that the same transaction may appear in more than one block. That might happen. Okay, so suppose these transaction blocks are getting created, miners have batching transactions into blocks, and let's say when a particular proof of work is achieved, they can send out those transaction blocks, right? So I'll just write that down. So transaction blocks have proof of work. So we've achieved one thing. We've managed to generate, let's say, these transaction blocks which are quite large. But good thing is that they don't have any particular ordering. So there's no such a thing as a fork among the transaction blocks, because anyway there is no blockchain structure over there. Okay? And that actually is an advantage, because if you have a strict blockchain structure as in Bitcoin, then these blocks have to be spaced really far apart, otherwise you're going to have a lot of forks. But by doing it in this fashion, you have these transaction blocks potentially coming very fast. So let's say that you have each transaction block can be 1 MB. You can have each of them coming out every 1 minute, a different transaction block, and you don't have to worry about forks, because there is no blockchain structure among them. So we eventually want to have some ordering of these transactions, because without an ordering, you don't really know what is there in the distributed ledger, right? What transactions are there? There has to be some sort of an ordering among them. You have to know which transactions are there in the ledger and what is their order. So we are partly going to solve that with something called proposer blocks. So these proposer blocks form a blockchain tree, something like in Bitcoin. So we start out with the genesis block, and then using proof of work, you extend the longest chain. Okay, so just like Bitcoin, you create these proposer blocks. You are trying to do proof of work on the longest chain that you've seen, and you generate these. You could have some forks over here, right, because you have a blockchain structure. Now these proposer blocks don't really have any transactions in them, so they are small in size, and a good thing about small blocks is that they propagate fast. Okay, so you could generate these, let's say, every 1 minute, and still you will have very few forks, because the size could be of the order of tens of bytes or hundreds of bytes, right? So how are they going to help? Well, we want to use them somehow to have an ordering of these transaction blocks. Okay, so what do we do over here? Each of these proposer blocks can point to one or more existing transaction blocks. For example, this one is pointing to these two transaction blocks. Okay, and of course there's a particular ordering of these transaction blocks within this, right? And so that gives us effectively an ordering of transactions, at least when this block is considered, right? Let's say that this one is listed before this, so the transactions in this block come before this one. Okay, and let's say this particular block points to these two transaction blocks. Okay, so it's possible that two proposer blocks might point to the same transaction block. Okay, just like here you had some redundancy, you could have two transaction blocks having the same transaction. Here you may have two proposer blocks pointing to the same transaction block. Okay, But effectively, honest miners will try to reduce this redundancy as much as possible. Okay, and we'll have to look at those rules a little bit later on. Okay, and so this one, for example, is not pointing to any of the transaction blocks pointed by these two. It is pointing to these other two transaction blocks. Okay, so to summarize, transaction blocks themselves don't have any ordering. They just list some transactions, some pending transactions among them. These proposer blocks, each of them can point to more than one transaction block, right? And this, at least within these, we have some ordering of transaction blocks. Okay. But eventually what we want to achieve is to get a, let's say, a total order among all these transaction blocks. And the question is, how are we going to do that? Okay. So let's think for a moment, thought process. Suppose we were just focusing on this particular proposer block tree. Can we come up with an ordering of these transaction blocks? Okay, so I'll give you an idea which is not used by Prism, but let's say that we take the longest chain over here. We use Satoshi's ideas. We focus only on these blocks in this longest chain, and that will give us some order among these transaction blocks, right? So for example, here we would have this one, these two, followed by these two, and so on, right? And then whichever transaction blocks these proposer blocks point to, right? And then we would have an ordering among the transaction blocks. In case that particular transaction block is repeated, we just only consider the first occurrence of that among the list of transaction blocks pointed to by all of these, right? And that's how we have an ordering among these, and that would give us our distributed ledger. Okay, so that solves the ordering problem, but what it doesn't solve is the confirmation time. So we still have a large confirmation time because we are using this longest chain rule. And Satoshi showed you would have to wait for something like 6 blocks, let's say, for a particular 6, let's say, subsequent blocks for any particular block to be confirmed in the blockchain, right? And until, let's say, this particular block is confirmed, we don't know the ordering of these, where they are going to be and so on. Somebody could launch an attack, and he could sort of get rid of this block, and then we would have to reconstruct the ordering among these transaction blocks. Okay. So what the authors of Prism wanted is not just a fast transaction generation time, which we've got over here. They also wanted a small confirmation time. Okay. So for that, what the Prism authors do is they use something called voting chains. So there are these third set of blocks called voter blocks, and how they are organized is in this fashion. You have multiple voting chains. Let's say you have n particular voting chains, right? And I'm listing them as G1, G2, and so on up to Gn over here. So each of these is its own blockchain. You have several of these voting chains. And of course, you could have forks over here. I'm not showing them just to simplify things, but you could have forks over here also, right? So here, when you're generating these, again you follow the longest chain rule, and if you find, let's say, a valid chain which is the longest, then you try to mine on that. Okay. So these voting blocks are also like proposer blocks, very small in size. Okay, they have no transactions at all, but these are not going to point to transaction blocks. They instead are going to vote for proposer blocks. Okay, and we want to do this voting in such a way that we are going to be able to confirm a proposer block really fast. We don't have to wait for the proposer chain to increase. very quickly we sort of figure out which proposer blocks are going to be there dominantly. Okay, so how are we going to do this? Each particular voting chain is allowed to vote for one block at a particular level in this proposer tree. Okay, so for example, this particular block has voted for this one. This particular block has voted for the next. He's not allowed to vote for this level 1 because it has already been voted for in his chain. He can vote for any of these, and let's say that he has seen this block first, so he votes for it. Now let's say it took some extra time to generate another block on this voting chain. So this block is allowed to vote for all levels which have not yet been voted on by ancestors in that particular voting chain. So there are two levels, let's say, which have of the proposer chain in which blocks have been created. So this one votes for one block at both these levels, okay, which I am showing over here. Okay. So notice one curious thing: it's possible for a particular voting chain to vote for blocks which are not on the same chain in this proposer block tree. For example, this one is not in the longest chain over here, whereas these others are in the longest chain. Okay, so though we are mining using the longest chain rule over here, which blocks are voted for in this proposer tree depends, on how votes are cast, and they don't all have to be in the same blockchain over here. They could be at different branches of the tree. Okay, so I've told you how the voting is done, but we still haven't decided which of these is going to be chosen as a leader. Okay. So we want to choose leaders at every level in the proposer tree. Okay, and we will only consider leaders at every particular level. We will not consider all blocks in a particular path necessarily, right? So for example, suppose this one ends up as a leader, we will consider this block and we will not consider this one at that particular level. Okay, and once we have leaders at every level in the tree, we can only consider those leaders and find out which particular transaction blocks they are pointing to, and thereby we get an ordering of the transactions. Okay. So how are we going to choose a leader at a particular level? I've told you how we have done voting in these different voting chains. So the rule is that rule to choose a leader at any level in the proposer tree is a block with the highest number of votes. Among the voting chains. So suppose n is 1000, so we have 1000 voting chains, and let's say this, okay, let's focus here where we have a fork. Let's say that this one got 501 votes and the other one got 499, let's say, right? So clearly this one has more votes, so it becomes the leader. Okay? But it's possible that you have, let's say, 3 blocks at a particular level in this proposer tree. Okay, and you would choose, let's say, out of 1000 votes cast, you would see which particular block has the highest number of votes, and that becomes the leader. Okay, so let's say that we mark the leaders over here. Let's say that we choose, okay, let's say that this is a leader. Let's say this one becomes the leader. Let's say that this becomes the leader, and so on. Okay, so each particular block here is allowed to vote for all levels which have not yet been voted for by its own chain, and if it is an honest miner, it will vote for the first proposer block it has seen at a particular level in the tree. Okay, so let's say that these are the winners according to that rule. Okay, of course, what if there is a tie? I haven't seen very clearly in the Prism paper how they deal with ties. Both of these got 500 votes. Then how are you going to decide, right? Probably you can use some tie breaking rule, like looking at the smaller hash among these and so on. Okay, so just to summarize how this is going to work, you have transaction blocks being generated. Okay, there's no order over here, so they can be generated very fast in time. We don't have to worry about forks. You have proposer blocks, right, where we follow the longest chain rule, and you do have a tree over here. So these also contain POW. Okay, so in fact all of these contain POW, the transaction blocks, the proposer blocks, and the voting blocks. Okay. Each of these can point to more than one transaction block, so we have at least some ordering. Within each of these blocks you have an ordering of, let's say, one or more than one transaction block. But to get the final order, we go to the voting blocks. We choose one proposer block as leader at every level in the tree over here, and this happens really fast. And why does it happen fast? Because let's say that you want to choose a leader over here, you don't have to wait for 6 blocks over here in the tree, right? Let's say right away you have, let's say, these 1000 blocks getting generated, let's say in a minute's time, and let's say out of them, let's say 600 have voted for this one. So you immediately know that this is the leader, okay, because you're just going by the rule that majority, actually the highest number of votes over here are going to decide who is the leader. Okay. So you might say, is it possible for an attacker to change somehow the leader, So suppose, let's say that you have let's say 501. Let's make it let's talk about an attack. So suppose we are looking at a proposer tree. Suppose this is B1 and this is B2. Suppose B1 has 501 votes and B2 has 499. So what is the attack that we do? You would want to change the vote of at least a couple of chains, let's say, a couple of voting chains. So how would you do that? Well, you could create a fork. The attacker, let's say, creates a fork somewhere over here, maybe a private chain. He generates a chain which is longer than these honest voting chains, and he kills those chains. and he changes the vote so that let's say the leader shifts from here to here. Okay. So how easy is it for him to do that? Well, it really depends on the difference. So the difference here is small. So an attack may be possible. Right? But suppose the voting was quite different. Suppose B1 had let's say 600 votes and B2 had only 400 votes. Then you can see it's going to be pretty hard for the attacker to change the vote, so that he might be able to change one or two voting chains by creating an artificial fork. But switching so many votes to the other side is going to be very difficult to do. Right? So it's a very robust system because you have so many parallel voting chains being created. It's very hard for an attacker to mess with a large number of them. Right? So by having a large number of chains, effectively we have made something like a private chain attack from an attacker. We are making it very, very difficult to for an attacker to succeed in doing this sort of an attack. Okay. So so these are very powerful ideas of Prism, and in a nutshell, this is what Prism is doing, right? So you have transaction blocks which are generated fast with a lot of transactions. You have a proposer block tree where the longest chain rule is followed. You have these voting chains also where the longest chain rule is followed. Okay, and we could in theory work without voting chains, but it's just that we would have a large confirmation time. But we are speeding up the confirmation time with these voting chains. Okay, so how would you know? Suppose you are just seeing all these blocks being generated. How would you know what is the ordering of transactions? So first thing you do is you go through these voting chains and you look at the votes and you figure out which are the leaders over here in the proposer chain, right? The highest vote number of votes essentially decides who's a leader at a particular level. There is just one vote cast for each level in each voting chain, right? Once you have these leaders, you look at which transaction blocks they point to, right? So you first start with this leader. You see that it points to these two transaction blocks. You see in which order it points to them. Right? So by point I mean it just has the hash of these transaction blocks. Right? And let's say this is the next leader at the next level. So the ordering would be 1, 2 and 3 over here. Right? So this is a repeat, so you just discard it. Right? And let's say this one is the next leader. Let's say that it points to this one, and so then you would have 4 over here and so on. Okay. Okay. So as soon as you have a leader at a particular level, you have you can move on to the transaction blocks and you get an ordering among the transactions. Right? So we get high throughput and low confirmation time at the same time. So how is the proof of work done? Because we said that even though you have these different types of blocks, all miners should be doing the same activity, the same sort of proof of work. And you probably have an idea of how this is done from the lectures on anchors and links, where we were simultaneously generating blocks and anchors. We didn't have a separate mechanism to generate them. So how to generate blocks, the various types of blocks. So what you do is you simultaneously mine for transaction block, proposer block, and n voting blocks. Okay. So what a miner does is he chooses transactions in transaction pool to create, he creates this transaction block. Okay. So let's say he puts all his transactions here. Okay, and transactions which have already been confirmed in the blockchain are not going to be there in his transaction pool, right? So these are really the pending transactions which are not already confirmed in the blockchain. So let's say that we have some sort of a Merkle root. Okay. And at the same time, we want to also be mining for a proposer block. So here, let's say you have hashes of transaction blocks. So let's say you have another root over here, Merkle root. Okay. And you also have voting blocks which you have to be creating. Okay, so you will also have, let's say, a hash of a previous proposer block, right? And you will also have to have n hashes of previous blocks in various voter chains. Okay. So all of this information has to be there in the block that you're trying to do POW on. Right, and so let's say that you have some sort of a header over here. So all this information somehow has to go in, and you would want to have some optimization scheme. You wouldn't want, suppose there are 1,000 of these, that's a lot of information, right? So you would want to have, let's say, a root of this itself. You won't want to put all of them in this header. Right? You do some sort of an optimization and put it in over here. Okay. And now we are going to do simultaneous POW. So this is a proof of work. This is 0 and this is 2 to the power of, let's say, 256 minus 1. So within this region, let's say you have transaction block created. If the hash lies here, if it's within this, then we say that a proposer block is generated. And then of course we have, let's say, n of these for voting chains. Right? So you keep hashing. And if your hash ends up in one of these, then you have created a certain type of block. Okay, so you might, suppose you end up here, then you have created a block on the nth voting chain. If you hash lies here, then you have created a block on the first voting chain. right? Or you may have created a transaction block or a proposer block. So just like we did with anchors and links, you don't have to transmit all the information every time you create one of these blocks. Suppose you have created a voter block for let's say the first chain. You don't have to send the transactions or this information and so on. You would just have to send out the minimum information to convey that you have indeed generated a voting block at that particular level, right? So of course, I think I missed out on some information. So in addition to the previous thing, you also have to have votes for proposer blocks, right? Okay. So you would have to give a Merkle proof, right? You would have to send out the header, of course, to show that the hash of this header is in a particular range, and you would have to send out appropriate information. Suppose you've generated a voting block for the first voting chain, you would have to send out the Merkle proof. You would give which votes, for example, and you would also have to give the previous block in the voting chain to which you are pointing to, and so on, right? So similarly, if you generated a proposer block, you don't have to send out transactions. You would only send out this information, right? And you would leave out the other information, right? You would send out the header and whatever minimum information you need to convince somebody that you have generated a block at a particular type of block and the essential information which that block contains, right? So it's a very complicated scheme used by Prism, but what they have achieved is that they have achieved high throughput and low confirmation time at the same time. Okay, so of course you might wonder, is it really going to work? Because there could be, let's say, forks or attacks possible. For example, I said that if you create enough forks over here, you might actually be able to change the leader at a particular level in the proposer blocks, and that would create havoc, right? Because if you change one leader here, then the whole ordering of transactions is going to change, right? So various attacks may be possible, but you can prove that if you have large enough number of voting chains, it's very hard for an attacker to change a large number of them, so that you actually will have a change in the leader. Okay? In case you have a 50-50 sort of a very narrow win for a particular block at a particular level, then you could be more open to an attack where the leader can actually be shifted, right? What also might happen is you may have redundancy of transactions in different transaction blocks. You also may have a case where multiple leaders are pointing to the same transaction blocks. Okay, so some redundancy could be there, okay, but eventually we will have some ordering of transactions and also fast confirmation time.